We live in a world where unevenness is a common characteristic. From the distribution of wealth to the size of cities, patterns emerge where a limited number of elements dominate the majority. This is not merely an observation but rather a phenomenon described by a mathematical model known as the Pareto Distribution.
The Pareto distribution, often referred to as the 80/20 rule or simply Pareto principle, is a very fascinating concept on its own. While we might envision a world where resources are evenly distributed, reality often presents a different picture. The Pareto distribution, named after Italian economist Vilfredo Pareto, helps us understand this unevenness. It highlights how a small percentage of elements frequently account for a disproportionate share of the total value.
This concept was first observed by Pareto himself, an Italian economist and sociologist in the late 19th century. While studying wealth distribution in Italy, he made a significant observation. A substantial portion of the country's wealth was concentrated in the hands of a small segment of the population. This discovery laid the groundwork for the Pareto distribution, a principle that continues to influence our understanding of various phenomena across diverse fields. The Pareto distribution provides a framework for analyzing how things are distributed, helping us to grasp the inherent unevenness that exists in many aspects of our lives.
This concept can be simplified further with the 80/20 rule, which states that approximately 80% of the effects come from 20% of the causes. At first, this was observed by Pareto himself when one day, while tending to his garden, he noticed that a few large peas in his pots made up of most of the pot's weight, while many smaller peas contributed very little. This observation sparked an idea in his mind. Could a small portion of inputs account for a large portion of outputs? Inspired by the peas, he investigated wealth distribution in Italy and discovered the same pattern, leading to the famous 80/20 rule, which is 20% of the people owned 80% of the land.
The same principle applies to real-world scenarios like traffic accidents, for example. When observing the accidents chart, it seems like a large number of drivers are responsible for the casualties, but in reality, only a small percentage of drivers are accountable to a large majority of accidents and injuries on the road. Even in factories and industries context, the major problem of pollution are caused by only a few production outputs of small number of factories.
The Pareto distribution is a mathematical model that describes the probability of a random variable exceeding a given value. The formula presented on this slide represents the complementary cumulative distribution function (CCDF) of the Pareto distribution. It quantifies the probability of observing a value greater than x for a random variable x within a Pareto distribution. The formula is defined in two parts, contingent upon whether the value x suppresses or falls below the minimum possible value xm. For x is greater or equals to xm, the probability is defined as xm divided by x to the power alpha. This indicates that the probability decreases as the value of x increases. For x is less than xm, the probability is 1 as xm represents the minimum value, and values below it are not possible within this distribution. The formula encapsulates the concept of unevenness inherent to the Pareto distribution. As the value of x increases, the probability of observing a value exceeding x diminishes, reflecting the concentration of probability towards the lower end of the distribution. This formula serves as a potent tool for understanding and analyzing the behavior of diverse phenomena that exhibit similar uneven distributions, including wealth distribution, city sizes, and website traffic.
Let's explore the process of deriving the probability density function (PDF) for the Pareto distribution, starting from its cumulative distribution function (CDF). We'll begin with the CDF, which tells us the probability of observing a value less than or equal to a specific point x in the distribution. The CDF is defined as for values of x is greater than or equal to xm is 1 minus xm divided by x to the power of alpha. for values of x is less than xm is 0, where xm is the minimum possible value in the distribution. Alpha is a shape parameter which determines how the distribution is. To obtain the probability density function PDF, we need to differentiate the CDF with respect to x. In simpler terms, we are finding the rate of change of the CDF. The PDF is expressed as the derivative of the CDF with respect to x. We'll substitute the CDF formula into this expression. Now we differentiate the term xm divided by x to the power alpha with respect to x. Again, we take the derivative of the term xm divided by x to the power alpha with respect to x. Simplifying the expression, we get the PDF is equal to alpha times xm to the power of alpha divided by x to the power of alpha plus 1 for values of x greater than or equal to xm. For values less than xm, the PDF is 0, but the Pareto distribution is defined for the value greater than or equal to xm. Combining the both cases, the complete PDF of the Pareto distribution is the PDF is given by for the value of x greater than or equal to xm is alpha times xm to the power of alpha divided by x to the power of alpha plus 1 for values of x less than xm is 0. This formula gives us the probability density of each value of x in the Pareto distribution. Understanding the PDF and its derivation is essential for analyzing and interpreting data that follows a Pareto distribution.
Now visualizing the probability density function of Pareto distribution, we can see that each curve in the chart represents a different Pareto distribution, each with a unique shape parameter that is alpha. Here alpha is taken like a dial that controls how steep the curve is. We can also notice that the curve with alpha equals to 1 is the steepest one. This means most of the probability is concentrated close to the minimum value that is xm. Now, as alpha increases, the curve becomes less steep. For example, the curve with alpha equals to 2 is less steep than the alpha equals to 1 curve, and the curve with alpha equals to 3 is even less steep. This shows that a higher alpha means the distribution is more evenly spread out, with a larger proportion of values further from the minimum value. This visual gives us the insight that the shape parameter alpha determines how likely we are to see different values in a Pareto distribution. A lower alpha favors extreme values, while a higher alpha creates a more even distribution.
Let's delve into the derivation of the cumulative distribution function CDF for the Pareto distribution. This formula helps us understand the probability of observing a value less than or equal to a specific point x within this distribution. We'll begin with the probability density function PDF of the Pareto distribution, which defines the probability density at each value of x. The PDF is expressed as for the value of x greater than or equal to xm is alpha times xm to the power of alpha divided by x to the power of alpha plus 1. For values of x less than xm is 0, where alpha represents the shape parameter which determines how the distribution is. Xm is the minimum possible value for the distribution. To calculate the CDF, we need to integrate the PDF from the minimum value xm to the value of interest x. We are essentially adding up the probability densities from the starting point xm up to the value x. We'll substitute the PDF expression and perform the integration using the power rule of integration. This step calculates the accumulated probability for values greater than or equal to xm. For values less than xm, the probability of observing the value less than or equal to x is 0. For values of x less than xm, the CDF is equal to 0. Finally, combining the result for the both cases, we arrive at a complete CDF for the Pareto distribution. CDF is defined as for values of x greater than or equal to xm is 1 minus xm divided by x to the power of alpha. For values of x less than xm is 0. This formula gives us the probability that the random variable x is less than or equal to the given value x in a Pareto distribution. Understanding the CDF of the Pareto distribution, it is crucial for analyzing various phenomena characterized by uneven distribution, such as wealth distribution, city sizes, or network traffic. This mathematical framework provides valuable insights into how probabilities are distributed and how to make informed decisions based on this understanding.
Now, let's explore another essential aspect of the Pareto distribution, that is its cumulative distribution function or CDF. Similar to PDF, each curve in the graph represents a different Pareto distribution, each with a unique shape parameter alpha. We already know that alpha controls the steepness of the curve, and the CDF tells us the probability of observing a value less than or equal to a specific point. Now, we can observe how the CDF starts at 0 and gradually increases towards 1 with the figure. The curve with alpha equals to 1 increases more slowly than the other curves. This indicates that for a given value of x, the probability of observing a value less than or equal to x is lower for alpha equals to 1 compared to higher values of alpha, which means that for a lower alpha, the probability is more concentrated near the lower values, while for higher alpha values, the probability is more evenly distributed across the range. The CDF helps us visualize how the Pareto distribution accumulates probability as values increase. It's a helpful tool for understanding the overall behavior of the distribution and for making predictions about the likelihood of different events.
While the 80-20 rule, a counterstone of Pareto distribution, offers a powerful framework for understanding uneven distribution, it's essential to acknowledge its limitations. Firstly, the exact proportions are not always a strict 80-20 split. Depending on the context, the ratio might be close to 70-30, 90-10, or even other variations. Secondly, focusing on the top 20% can lead to overlooking the remaining 80%, which might still hold significant value in a specific scenarios. Finally, it is crucial to remember that the Pareto principle is a general observation, a valuable tool for understanding unevenness, but not a guaranteed solution for every situation. It's essential to combine the Pareto principle with data analysis, informed decision-making, and a flexible approach to achieve optimal results.